In this lecture, we are going to continue the discussion of dimensional analysis. In the dimensional analysis, we talked about the pi theorem or Buckingham pi theorem, that how do we choose or how do we find out the non-dimensional groups for a particular problem using the repeating variable method. Okay. So, if let us look at a different problem which talks about that when a capillary tube is dipped in a liquid pool. So, if you have pool of liquid which is filled with some liquid, let us say water, and a capillary is dipped in this pool of liquid. Now, because of the contact angle, the water will rise in this capillary and the height of this water rise in the capillary is, let us say, delta H. The specific weight of this liquid gamma, which is basically a product of density of the fluid and acceleration due to gravity. So, the liquid rise in capillary delta H depends on the diameter of the capillary, which is d, the specific weight of the capillary and surface tension. Okay. Of course, it will also depend on the contact angle, but that will give us a non-dimensional number anyways. So, what we need to do is combine these and find a set of non-dimensional parameters. So, we have that delta H is a function of capillary diameter d, the specific weight gamma and surface tension sigma. So, let us start with writing out the dimensions of these. So, the dimension of H is L, which has dimensions of length. D again has the dimension of length. Sigma is dimension of force divided by length. So, m L T minus 2 divided by L, which is m T raised power minus 2, and the dimension of sigma is rho into g. So, m L raised to the power minus 3 into L T raised power minus 2. So, this gives us the dimension of gamma is equal to m L raised to the power minus 2 T raised to the power minus 2. Now, the number of primary dimensions, in this case we have 3 primary dimensions m, L and T. So, the number of primary dimensions are 3. So, if we use our previous theory, then the number of repeating variables should be equal to 3, but is that so? So, if we look at that, if the number of repeating variables are 3, then the independent variables that we have here is these 3 variables can be d, gamma and sigma. So, if you try to find a dimensionless group from this, but before that one condition is that these repeating variables should not form a group among themselves. A small inspection will tell you that gamma is m T raised to the power minus 2. So, the dimension of sigma is m T raised to the power minus 2. So, if you look at the gamma, which has dimension of m L T raised to the power minus 2, which is sigma over d squared. So, if you see the dimension of sigma is m t raised to the power minus 2, dimension of d is L. So, d square L square. So, you can form a non-dimensional group, sigma over gamma d squared is a non-dimensional group in itself. So, the condition or the requirement that the repeating variables should not make a dimensionless group among themselves is not satisfied here. So, what is the problem? Let us revisit the pi theorem. The problem lies here. If we look at the dimensions of sigma, which is m t raised to the power minus 2, and dimensions of gamma, which is m L raised to the power minus 2 and t raised to the power minus 2. The dimensions of m and t are same in both the cases. So, m raised to the power 1, t raised to the power minus 2, m raised to the power 1, t raised to the power minus 2. So, they are going to be same. So, that will not help. Now, the cases like this, they will arise very rarely. Most of the problems, the theory that we developed in the previous class, that the number of repeating variables will be equal to the number of primary dimensions, will hold good for most of the problems except a few. So, in most of the cases, that is true, that the number of repeating variables m is equal to number of primary dimensions r. Then the more fundamental definition or the more fundamental principle is that the value of m, it will be the rank of dimensional matrix. So, just to remind ourselves that the rank of a matrix is equal to order of largest non-zero determinant. So, if you make a determinant from the dimensions of the matrix, then the rank of such a matrix will be the value of m. Okay. So, let us revisit the problem again. We have delta h is equal to f d gamma sigma, function of d gamma sigma. So, the dimension of h is L, the dimension of d is L, dimension of gamma is m L raised to the power minus 2 t raised to the power minus 2, and the dimension of sigma is m t raised to the power minus 2. So, we can make a dimensional matrix, and to make the dimensional matrix, what we need to do is can write in a column the dimensions m l t for all the variables. So, delta h d gamma and sigma. So, for delta h, what we are going to write, the values here will be the power raised on m, l and t for each variable. So, for delta h, the dimension is L. So, m raised to the power 0, L raised to the power 1 and t raised to the power 0. For d, m raised to the power 0, again L raised to the power 1 and t raised to the power 0. For gamma, 1 minus 2 and minus 2, it is 1 0 and minus 2. If we take the largest determinant, in this case, if we take a determinant from this so this is the dimensional matrix. Okay. From this dimensional matrix, if we take the largest determinant, which will be of if we take 0 1 1, 1 minus 2 0 0 minus 2 minus 2. So, the value will be 0 minus 1 into minus 2 minus 0 plus 1 into minus 2. So, this will come out to be 2 minus 2, which is equal to 0. So, this cannot be a matrix, cannot be of rank 3. So, let us check the next smaller matrix, which is minus 2 0 minus 2 minus 2, and its this determinant, the rank of matrix will be, if this is non-zero, then the rank will be 2. So, let us see 4 minus 0 is equal to 4, which is non-zero. So, the rank of this matrix is equal to 2. So, that means the number of repeating variables is equal to 2. So, if we choose 2 repeating variables in this, the delta H is function of d gamma sigma. So, from that we will be able to find delta H by d as one non-dimensional group, and the other non-dimensional group, as we just saw, that we can form a non-dimensional group from the 3 of these. So, sigma over gamma d squared m l raised to the power minus 2. So, m t minus 2. So, these will be 2 dimensionless groups, delta H by d and sigma by gamma d squared. Okay. So, that is a limitation or a complexity in pi theorem. Still, this is the most popular method which is used for dimensional analysis. Now, there is another method which is called step by step method, and which is one is likely to follow this step by step method if one is doing it in a sequential manner, just by using, say, common sense. So, the Ibsen's method is called step by step method, and it is basically based on eliminating each dimension by division or multiplication. So, by looking at the variables, you tend to divide, you write down the dimensions, and then you tend to divide one by one by the variables, so that the dimension for each, the power for each dimension m, l and t, or other fundamental dimensions or primary dimensions, the power is to them become 0. Okay. So, let us take the common example that we have been taking, that the drag force on a sphere is a function of the diameter of the sphere, the velocity, relative velocity between the fluid and the sphere, the density of fluid and the viscosity of fluid, and we write down the dimensions of these. So, dimension of force is m l t raised to the power minus 2, dimension of diameter is L, dimension of velocity is L t raised to the power minus 1, density is kg per meter cube. So, m L raised to the power minus 3, the unit of viscosity is kg per meter per second. So, m L minus 1 t minus 1. Now, what we need to do is we can start eliminating the dimensions. So, we can start eliminating m, L and T one by multiplying or dividing, as the case may be, by those variables which has the dimensions by which to divide. So, for example, here let us say if we want to eliminate m, we start by eliminating m. So, we can choose density and we can divide by density to all those variables which contain m. So, we can divide f by density. So, f by rho, these two variables d and v, they do not have m there. So, we do not divide them, then rho by rho. So, this becomes dimensionless, we do not need to consider it anymore, and mu by rho. So, we have eliminated m from these variables and we are also one variable down, we do not need rho anymore. Then we can keep doing this thing. We need to remember, or we need to note here, that the division is required for only those variables which have the dimension by which to divide. So, basically this is one step ahead of inspection. It puts a sequence to the division by inspection or forming dimensionless groups by looking at the dimensions only or dimensions itself. So, if you write down this problem and let us try to solve it. So, if we divide by m, so let us divide by rho, we need to and we are doing this to eliminate m from each dimension. So, if we do it f by rho, and that will be a function of d remains same, v remains same, and we will have rho by rho. So, we actually this variable will has become dimensionless, and then we have mu by rho. And let us write down the dimensions again. So, this will have dimension now m l t raised to the power minus 2 divided by rho, which is m l raised to the power minus 3, and m and cancel out. So, what you have is l raised to the power 2 t raised to the power minus 2, d is l, v is l t minus 1, and mu over rho. So, that becomes m l minus 1 t minus 1 divided by m l raised to the power minus 3. So, m and m cancel out here, and you have l squared t raised to the power minus 1, and if you remember, this is mu by rho is kinematic viscosity. Now, we have been able to successfully eliminate m from these dimensions. So, let us try another variable t, and for t we will choose velocity v. So, let us eliminate t. So, to eliminate t, let us divide by velocity v. So, we have to divide or multiply in such a manner that the dimension of time is eliminated. So, this has time raised to the power minus 2, whereas velocity has time raised to the power minus 1. So, we will divide by velocity squared f over rho v squared, L remains same. So, that will be a f over rho v squared will be a function of d, again v by v. So, this has become dimensionless and we do not need to consider it anymore, and mu there is time raised to the power minus 1. So, mu by rho we will divide it by V only. Now, the dimensions, if we look at the dimensions for this group will be L square t raised to the power minus 1, and we have divided by L V squared. So, sorry, this should have become L raised to the power 4, 3 plus 1 4. So, now we have the dimension of this will be L squared, L raised to the power 4 t minus 2 divided by L square. So, this becomes L square. The dimension of D is L, and mu by rho will have the dimension of again L squared t raised to the power minus 1 divided by L t raised to the power minus 1. So, we will have dimension of L. Now, we need to eliminate only L. So, we can divide by D. So, to eliminate L, let us divide by D. So, we will have F over rho V squared D squared, that is equal to function of D by D. So, it will become dimensionless and we will not consider it anymore, and mu by rho V D, because L has just one dimension or one power to it. So, we will divide by D. So, we are able to find two dimensionless groups F over rho V square D square, which is Dirac coefficient, and inverse of Reynolds number mu over rho V D. So, without finding any repeating variable, we have been able to identify the dimensionless groups. So, the number of restrictions that we had, that we need to look at the repeating variables. We need to find out the if the repeating variables are they making a dimensionless group, or is the rank of the dimensional matrix is equal to the highest rank, or is M is equal to R or not. So, all those restrictions are not there in Ibsen's method. We have looked at for non-dimensionalizing the groups, we can just write down the dimensions and try to find out as you become more experienced and try to see the dimensionless groups. You can do it by inspection only, you can do using Pai's theorem, or you can do using Ibsen's method. What we are going to do now is look at the fundamental governing equations for fluid flow, for an isothermal flow, and try to non-dimensionalize those differential equations which are called Navier-Stokes equations. So, the goal is that we familiarize ourselves at the start of course itself with the Navier-Stokes equations, and at the same time we non-dimensionalize them and see that the dimensionless groups appear naturally when we non-dimensionalize these equations. Okay. So, if we write down the mass conservation equation, which is dou rho by dou t plus del dot rho v. So, del rho by del t is partial derivative of rho with respect to time. If we write down this in Cartesian coordinate, then as we saw when we defined del dot v in the lecture on vectors, we can write down dou rho by dou t plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w. Okay. The momentum conservation equation, we will consider here the case for a Newtonian fluid. So, the constitutive equation, the relationship between the stress and strain is linear, and that has been used in this equation. So, this is the Navier-Stokes equation or the momentum conservation equation for a Newtonian fluid. So, the first term is the transient or unsteady term, which is time dependent term dou by dou t of rho v. The second term represents the convection of the fluid or the convection of the momentum because of the bulk flow. The first term on the right hand side is pressure term, next term is the viscous term, and the last term is the term due to gravity or other body forces. So, if you look at or as we read later on with the term on the left hand side basically represents the acceleration multiplied by mass per unit volume. So, if you have a rho which is mass per unit volume multiplied by the acceleration, and these are different forces that are acting. So, pressure term, viscous term and gravity term, which are all again in terms of force per unit volume, the units are. So, pressure, viscous are the surface forces, and gravity or any other body force that might be acting, they will be taken into account in the form rho g. So, that is these are the governing equations. If we write down momentum conservation equation in Cartesian coordinate system, we can expand this. So, what we are going to do is look at the we take a conservation equation, momentum conservation equation, let us say for x, and simplify it for a 2-dimensional steady flow and try to non-dimensionalize it. Okay. So, if we consider the x momentum equation for incompressible steady 2D flow. So, let us write down the x momentum equation first. The same thing we have unsteady term, and that 3 term represent the convective acceleration and then the forces. Now, if we do it for a steady flow, so the first term, because it is time dependent, so that will become 0, and because it is 2-dimensional flow, so W will be 0 and del 2 by del z 2 will also be 0. So, our equation will simplify and we consider flow to be incompressible. So, and density is constant. So, we can take rho as constant, and this comes out. So, rho u del u by del x plus v del v by del u by del y is equal to minus del p over del x plus mu del 2 u by del x 2 plus del 2 u by del y 2 plus rho g x. Now, we need to non-dimensionalize this. So, let us consider the scales for each of these variables. So, we have length variables x and y. So, these variables we will non-dimensionalize by a length scale of the problem, let us say L. The velocities in the flow u and v, we will non-dimensionalize by a velocity scale v, and the pressure will be non-dimensionalized by dynamic pressure, say rho v squared, which again will have unit of pressure. So, the dimensionless variables we will represent with a asterisk. So, x star is equal to x over L, y star is y over L, similarly u star is equal to u by velocity scale v, v star is equal to v over capital V, and the dimensionless pressure P star is equal to P divided by rho v square. Now, what we need to do is substitute these here the values of x. So, in place of x we will write x star L, in place of y y star L, and so on, and then collect the scales together. Okay. So, when we substitute it, what we get when after substitution. So, let us look at the first term u del u by del x. So, this u del u by del x term, when we write, u will be u star into v. So, you have 2 u in the numerator. So, that will be v star v squared and 1 x in the denominator. So, v squared by L into u star del u star by del x star. Similarly, the second term v del u by del y, that will be equal to v squared by L into v star del u star by del y star. The terms here in the viscous terms. So, del 2 u by del x 2 will be, you have 1 u here. So, v and x squared. So, L squared v by L squared del 2 u star divided by del x star squared. Then if we look at del p by del x. So, p will be rho v squared multiplied by p star and x you have. So, 1 L will come here. So, del p by del x will be equal to rho v squared by L into del p star by del x star. So, let us substitute these terms here. What we will see from these two terms, we can collect v squared by L outside the bracket. So, we will have the left hand term as rho v squared by L and within bracket u star del u star by del x star plus v star del u star by del y star. Now, coming to the right hand side, the first term as we saw del p by del x. So, we can substitute, that will be equal to minus rho v squared by L into del p star by del x star. The viscous term. So, mu is already outside the bracket and these two terms for del u 2 by del x 2 and similarly for del 2 u by del y 2, we will have v by L squared multiplied by within bracket del 2 u star by del x star squared plus del 2 u star divided by del y star squared plus rho g x. So, let us arrange the equation a bit. So, we can multiply by L by rho v squared. So, you will have left hand side u star del u star by del x star plus v star del u star over del y star. Rho v square by L, when you divide by rho square by L, this term will cancel out. So, you will have or you will be left with minus del p star by del x star. When you divide this mu v by L squared divided by rho v squared by L. So, you will be left with 1 L in the denominator, mu will remain in the numerator and in the denominator you will have v squared and 1 v at the top. So, in the denominator you will have 1 v and 1 rho because of the rho present here. So, this rho will come in the denominator. So, you will have mu over L rho v and within bracket the same term will come here and the last term rho g x divided by rho v squared by L. So, L goes up, rho will cancel out and you will have g x L by v squared. Okay. So, you can see that this is mu over L rho v is inverse of Reynolds number and g x L by v squared or v square by g L is Froude number of Froude number raised to the power minus 2. So, you have by non-dimensionalizing the equations you can find out the non-dimensional numbers. When you are talking about other non-dimensional numbers, for example, if you consider the transient term, you can get another non-dimensional number. If you non-dimensionalize the boundary conditions, then you can get another non-dimensional number. So, the non-dimensional numbers can also be found out when you non-dimensionalize the governing equations as well as boundary conditions. So, now we know quite a few methods which we can use to dimensionalize non-dimensionalize a problem. We can look at the variables and try to see by looking at their dimensions itself, we can try to form some dimensionless groups. when we become more experienced and we know about more dimensionless numbers, we can try to relate the relationship between the variables with the non-dimensional groups. We can use Buckingham Pi theorem using repeating variables, we can use Ibsen's method, or when we know the problem itself, we should try to see and find out what are the relevant dimensionless number from for a particular problem from the by non-dimensionalizing the governing equations. Thank you. So, we will stop here.